Here we're going to formalize some of the ideas we used in earlier examples. So we've seen already the multiplication principle. Now we have the idea of the addition principle. So suppose we have a finite set X that can be broken down into a few non-overlapping parts, which we'll call X sub 1, X sub 2, all the way through X sub n. All right, so we have n non-overlapping parts of set X. And this set can be completely broken down into these small parts. That is, suppose we have a situation like this. We have a big set X, and it can be completely broken down into n different parts, n different subsets, you might say, and there's no overlap among them. So here's a more formal way of putting it. That is, suppose we have a finite set X such that X is equal to X1 union X2 union all the way through Xn. So the union of X1 through Xn, that is X, right? So in other words, these little sets, X1 through Xn, put together compose X, right? X is composed of these smaller sets put together. And we also need the restriction that there's no overlap. So how do we state that? Where X sub I intersected with X sub j is equal to the empty set whenever I is not equal to j. That is, whenever we have two different sets, let's say X3 and X15, there is no overlap, meaning their intersection is the empty set. Okay, so suppose we have a finite set X such that X is equal to the union of X sub 1 through X sub n, where the intersection of X sub I and X sub j is always going to be the empty set whenever I is not equal to j. Okay, so again, so far I haven't stated anything. This is all a supposition. Suppose this. Okay, so what are we trying to say? Then, okay, so if we have these, if we have this supposition, if we are working in this world, then the cardinality of X, right? Suppose we want to find the cardinality of X. That's what we want here. We want to find the cardinality of X. The cardinality of X is equal to the cardinality of X sub 1 plus the cardinality of X sub 2 plus plus the cardinality of X sub n. So in other words, you take all these little sets, which together make up X, right? You take these little sets and you add them all up. You add their cardinalities up, and that gives you the cardinality of X, right? So, it seems a pretty, like a pretty obvious idea, maybe, but it's very useful for use in counting problems. And although we haven't stated this principle until now, we've actually used this in an earlier example, specifically part C of the long example from the previous video. So let's go back to that example and let's redo it in using this language of the addition principle. So here's the example. This was again part C from the previous video. How many length 4 non-repetitive lists? So again, we're talking about lists of length 4 without repetition allowed. How many such lists can be made from the symbols A, B, C, D, E, F, and G if the list must contain an E? Okay. So let X be the set of all length 4 non-repetitive lists made from the symbols A, B, C, D, E, F, and G that contain an E. All right, so the set X is the set of all the lists that we are interested in. Right, that's so we want to count how many things are in X. In other words, we would like to find the cardinality of X because X is the set of all lists that we are interested in counting. So we just need to find the cardinality of X. Now, each of the lists in X must contain exactly one E. Now, why is that? Why does each list in X have to contain exactly one E? Well, we specified that X is the set of all lists that have to contain an E. So they have to contain at least one E. How do we know that it's exactly one E? Well, we also said that they're non-repetitive lists, meaning within a list, no repetition is allowed. In this particular example, I mean, in general, lists can allow repetition, but in this particular example, lists are not allowing repetition. So we know that each list must contain exactly one E. It has to contain an E and not more than one E because then it would be repetition. Okay, so if each list must contain exactly one E, that E will either be the first, second, third, or fourth entry. So let us define the smaller sets, right? Remember, when we use the addition principle, we're trying to break up this big set X into a bunch of smaller parts. So let's break it up into 4 parts. So for I equals 1, 2, 3, and 4, let X sub I be the set of all length 4 non-repetitive lists made from the symbols A, B, C, D, E, F, and G, where the ith entry is an E. Right, so we're going to be creating 4 smaller sets. And so the first set is going to have E as in the first entry. The second set is going to have E in the second entry, and so on. Right. So for example, let X sub 3, right? We're defining these X sub 1, X sub 2, X sub 3, and X sub 4. So for example, let X sub 3 be the set of all length 4 non-repetitive lists made from the symbols A, B, C, D, E, F, and G, where the third entry is an E. Right, so we similarly will define X sub 1 and X sub 2 and X sub 4 along with X sub 3. But that's just an example. So now we want to find the cardinality of X. Well, we can find the cardinality of each of these little sets and then add them up. So the cardinality of each X sub I is 6 times 5 times 4, or 120. Why is it 6 times 5 times 4? Because we're making a list of length 4, and we use E for one of the entries. So for the other 3 entries, well, for the first empty entry, we have 6 choices, and then for the next one we have 5 choices because repetition is not allowed, and then for the next entry we have 4 choices because again repetition is not allowed. So using the multiplication principle, we come up with 6 times 5 times 4, or 120, as the cardinality of each of these smaller sets. Right, so X sub 1, X sub 2, X sub 3, and X sub 4. So each one has cardinality of 120. Now we note that X is equal to the union of X1 with X2 with X3 and X4. Right, the union of those 4 sets is equal to X itself. And there is no overlap among these little sets. Right, among the X sub I's, there is no overlap because for example, if the elements in X sub 1 have an E only in entry 1, so that's different from all the other sets. X sub 2, the elements of X sub 2 have an E only at position 2. The elements of X sub 3 have an E only at position 3. Right, and the elements of X sub 4 have an E only at position 4. So there cannot be overlap among X sub 1 and X sub 2 and X sub 3 and X sub 4 because they're all different. Okay, so therefore, thus by the addition principle, the cardinality of X, which is what we're trying to find, the cardinality of X is the cardinality of X sub 1 plus the cardinality of X sub 2 plus the cardinality of X sub 3 plus the cardinality of X sub 4. The cardinality of each of these smaller sets is 120. So if we add them up, we get 480. Another example of the addition principle. How many even 5-digit numbers are there for which no digit is 0 and the digit 6 appears exactly once? Okay, so again, we're trying to count even 5-digit numbers where there is no 0 anywhere in the number, and the digit 6 appears exactly once in the number. So for example, 55634, right? 55,634. That's a valid number. It's a 5-digit number. None of the digits is 0, and the digit 6 appears exactly once. Also, 16,118. That's also a valid number in this example, right? We're trying to count all such possible numbers like this. But let's just to be clear, let's give examples of numbers that we're not trying to count. So these are 2 such numbers, but not 63,304 because it has a 0, which we're not allowing in this. We're not trying to count such numbers in this example. Nor will we allow 63,364 because it has more than 1 6. Nor will we allow 55,637 because it's not even. Okay, So let X be the set of all such numbers, right? All such numbers, meaning all 5-digit numbers for which no digit is 0 and the digit 6 appears exactly once. Okay, so this X is a set that contains all of those numbers. Now, how big is X? That's what we want to know. We want to find the cardinality of X. So let X equal X sub 1 union X sub 2 union X sub 3 union X sub 4 union X sub 5, where X sub I is the set of each 5-digit, is the set of even 5-digit numbers for which no digit is 0 and the digit 6 appears only in position I. Right? So to find the cardinalities of each of these sets, we'll consider the number of choices that we have for each digit. So let's talk about X sub 1. So remember, X sub 1 is the set of even 5-digit numbers for which no digit is 0, and the digit 6 appears only in position 1. Position I, well, for X sub 1, I is 1, so position 1. So if we look at X sub 1, there has to be a 6 in position 1, and then we have 5 other digits. Question is, how many choices do we have for those other digits? Well, for the one after the 6, we have 8 choices. That's what this 8 means. We have 8 choices. Why 8 choices? Because we cannot use a 6 again, because there has to be exactly one 6. So we used 6 already, so we cannot use it again. Also, we cannot use 0 at all in the number at all, right? 0 appears nowhere in the number. So this cannot be 0. So we're left with 8 digits to put in, 8 possible digits to put here. The next digit can also be any of the 8 digits except any digit except for 0 and 6. So we have 8 choices. Again, repetition is allowed. That's not a problem for this particular example. The next digit again has 8 choices. Now, how about the last digit? Well, the last digit, remember that the number must be an even number. In order for a number to be even, the last digit must be either 0, 2, 4, 6, or 8. Now, we know that this last digit cannot be a 6 because we already used the 6, and it cannot be 0 because 0 cannot appear anywhere in the number. So we only have 3 choices left, right? The only choices that we could use for the last digit are 2, 4, and 8. So that's the question. So again, we're trying to figure out what is the cardinality of X sub 1. Well, we see that for the number, we have a certain number of choices for each digit, right? So we're going to use the multiplication principle, and using that, we're going to see that the cardinality of X sub 1 is going to be 8 times 8 times 8 times 3. Okay, we'll come back to that. Let's go on to X sub 2. So X sub 2 is the set of all even 5-digit numbers for which no digit is 0 and the digit 6 appears only in position 2. Right, so we have the 6 here. We have 8 choices for the first digit because it could be anything except for 6 and except for 0. 8 choices for this digit, 8 choices for this digit, and again, 3 choices for the last digit for the same reason as in X sub 1. Going on to X sub 3, very similar situation. X sub 4, very similar situation. Now X sub 5 is a little bit different. So X sub 5, we have 8 choices for the first digit, 8 for the second, 8 for the third, and 8 for the fourth. So we have 8 choices for each of the empty digits. Because we know there's a 6 here already. We don't have to choose anything. We have only one choice for the last one, which is 6. So we don't have to worry about how many even digits can we use there. Okay, so thus we want the cardinality of X. That's going to be our answer. Well, the cardinality of X is equal to, well, we'll use the cardinality of X sub 1 plus the cardinality of X sub 2 and so on. So the cardinality of X sub 1 is 8 times 8 times 8 times 3. Now we add the cardinality of X sub 2, which is 8 times 8 times 8 times 3. Then we add the cardinality of X sub 3, which is 8 times 8 times 8 times 3. Then we add the cardinality of X sub 4, which is, again, 8 times 8 times 8 times 3. Then we add the cardinality of X sub 5, which is 8 times 8 times 8 times 8, not times 3. And multiplying and adding all this together, we get 10,240. So that's our answer. Now we have a different idea, the subtraction principle, and just like the addition principle, we've used this before without clearly stating that we were using it. So suppose a set X is a subset of a universal set U. Okay, so we have a set X, which is a subset of a larger set, which we'll call U. That is, suppose we have a situation like this, right? So we have U, we have this big set on the outside. And then we have this little set x in the inside. And then remember that we have this gray area here is the complement of x, right? X complement, right? We did, x with a bar on top, which is the universe minus x, right? So everything in the universe except for x. That's the gray area here. So suppose we would like to find the cardinality of x complement, right? In other words, suppose we want to find the cardinality of this gray area. In other words, suppose we want to find the cardinality of the universe minus x, meaning I want to know how many things are in the universe, not counting those things that are in x. So the subtraction principle says, and it seems fairly obvious perhaps from the diagram, but the subtraction principle says that this cardinality is the cardinality of the entire universe minus the cardinality of x. So in other words, if I want to count how many things are in this gray area, I can first count how many things are in the entire universe and then subtract from that the number of things that are in x. And that will leave me with the number of things in the gray area. So this is, when do we use the subtraction principle? So use the subtraction principle in situations where it is difficult to count the number of things that interest you in a set U, but it's easier to count the number of things in U that you aren't interested in, right? So suppose it is easy to count x, but I'm not really interested in x. I'm interested in U minus x, right? I'm interested in this gray area, but it's very easy to count this white area. So then if we can use the subtraction principle, it might be very helpful. So we don't have to manually count the things that are in this gray area. We can simply use the cardinality of the entire universe and subtract the cardinality of x from that, and that will leave us with the cardinality of this gray area. So here's an example, and this is just an example that we did already. This was part D from the previous video. But now we're going to redo it using the language of the subtraction principle. So the example was, how many length 4 lists can be made from the symbols A, B, C, D, E, F, and G if the list must have at least one E and repetition is allowed? So let U be the set of all lists of length 4 made from A, B, C, D, E, F, and G. Right? So whether they contain any or not, any list of length 4 made from these symbols, that's the universe. So the universe is much larger than what we're interested in, right? It includes or does not include, sorry, it includes those things, it includes lists that have E and includes lists that don't have E. That's the universe, that's the large set, the large outer set. By the multiplication principle, the cardinality of U is 7 times 7 times 7 times 7, right? Because each list in U can, for each list, we have 7 choices for each entry. Now let X be the subset of U containing all the lists that do not have any E's. Now, notice this is not what we're actually looking for in the question. What we're looking for is how many lists that have at least one E. But X is the set is the set that of all, is part of U, it's part of the universe, it's a subset of the universe, but it contains all the lists that do not have any E's. Okay, but this will be easier to count. By the multiplication principle, if you cannot use any E's, the cardinality of X will just be 6 times 6 times 6 times 6. There's an extra dot here. That's a mistake. Okay, this dot should be removed. Okay. We are interested in the subset of U containing all the lists that have at least one E. In other words, what we're interested in is the complement of X, not X, but the opposite of X, the complement of X, meaning everything in the universe except for X, U minus X. That's what we're interested in. By the subtraction principle, the answer is the cardinality of U minus the cardinality of X, which is 2,401, minus 1,296, which is 1,105. And that's in fact the answer that we got in part D of the previous video.